Hi there. Here's the GEO-BOOST-7000 stand for your attention. The machine is designed for calibrating turbochargers in static mode and for testing and tuning turbochargers in dynamic mode. It connects to a three-phase 380-volt electrical network. No other connections are needed. This component is in charge of setting the turbocharger in static mode. There are adapters for calibrating and installing turbochargers, support for fixing the turbocharger rotor, and, naturally, the stand for purging and measuring the airflow through the turbocharger itself. The monitor is duplicated. This area of the machine is intended for dynamic mode setup. We connect the oil, install the turbocharger, connect the inlet to the turbine, which is the hot part, and connect the compressor section. This area has a connection for the ATP-1000 device for electronic turbines. Additionally, there are sockets for connecting the N75 valve for testing purposes, which is also available on the GEO-BOOST 2000 machine. This section of the machine is comparable to the GEO-BOOST 2000 machine, which includes the N75 valve testing function. The nodes are identical, and this part functions the same as this machine. We'll set the turbocharger statically. We need to calibrate the stand first. Let's install the adapter, and also place the calibration plate through the rubber piece. We press calibration. We select the turbocharger number. Now we are building the graph, the geometry setting characteristic and the boost setting characteristic. We are about to set the vacuum level at which the geometry begins to open. Notice that the graph is offset. It can be corrected. The turbocharger is set. The white line is the original, and the red line is our adjustment. We will now verify the settings in dynamic mode. We have turned on the oil. Oil pressure is visible. Turbocharger connected. We need to start the GEO-BOOST program now. The oil is on. Click the graph icon. Now we will load the test plan. Here we can see the performance of the car this turbine is put with. Engine size, horsepower, RPM at maximum power, turbine wheel diameter, compressor wheel diameter, and valves per cylinder. And altitude above sea level. These are the test plan data. We are checking the geometry settings. Let's start. Turbocharger preheating is about to begin. Don't forget to connect the vacuum. We are showing that the turbine is heating up and the performance is increasing. Now we will have a straight section. We can see that the turbocharger has warmed up. You may switch it off. We have now checked the geometry settings of this turbocharger in dynamic mode. We can see that the geometry settings have shifted slightly. The geometry is a bit constrained and needs to be loosened. Entering geometry adjustment mode. Starting now. Now the turbocharger is set up. We will now check the turbocharger's performance. For this, it is necessary to install the speed sensor. Apply a mark on the impeller with correction fluid. Mark the turbine wheel. Use a regular correction fluid. School corrector, office corrector. Before marking, we need to degrease that blade with gasoline. Drying it now. And we apply the mark. Mark the entire blade, not just a part. When installed on the car, the corrector burns out. It's not a big deal. No harm to the balancing. Choose the performance mode now. Press start. The graph shows that the turbocharger performs significantly better than the tolerance. At 154 horsepower, by substituting a different power level, we can gauge the quality of the turbocharger. It can produce about 175 horsepower. Here are the boost specs. The outcome is 0.9 kilos. This represents the relative pressure in relation to atmospheric pressure. So, absolute pressure is 1.9. This is the tolerance zone that we can see on the graph. Let's connect the turbine with the electronic actuator. Align the hole. Oil is on, oil pressure is visible. Like this. The USB connects here. We'll choose electro. It should be ATP 1000 OK. You can choose the percentage range to check here. We'll set it to 20%. Set this to 95. Because we already know that its operating range is from 5 to 95%. Let's see. We enter the turbine number, so this is ours. Loading now. Here's our chart. Our test plan. We are checking. We neglected to put in the speed sensor, and the system reminded us. The machine has warmed up. We can turn off the heating now. This is the data calculation for this turbine. Here are the output parameters we have: engine displacement, horsepower, RPM at maximum power, and the diameter of the turbine wheel. Compressor wheel diameter, valves per cylinder, and altitude. We are examining the graph now. It indicates that the turbocharger delivers power exceeding 180 horsepower. Allowing for some adjustments. 194 horsepower, compared to the set 180. This shows what this turbocharger is capable of. Boosting capacity, 0.9 kilogram, relative to atmospheric pressure. Tolerance, 1 to 0.77 kilogram, relative to atmospheric pressure. Is how many kilograms per hour the turbocharger will blow at a given pressure. At maximum power RPM, This relates to performance verification. As for the geometry adjustment of the turbocharger, it is within acceptable limits. On this type of actuators, adjustment can only be done by rotating the snail. Programmable actuators allow angle adjustments through programming. Let's check the adjustable geometry settings in static mode. Turbo with electronic actuator. Manual test. We check the actuator's functionality for any jamming or inadequate operation. Connect it to the machine. The device is restarting. We must choose our actuator again. The PC is illuminated, meaning the device is linked to the computer. Select the turbine number. We are able to see it now. It shows 78%. It should be 66. We also need to switch from pneumatic to electric. A hint is provided above. What should be done? Change the language option. Position the actuator to match the fully closed geometry and then press the start button. The geometry is maximally closed. Press start. The device shows 78%, and the turbine is within acceptable limits. We can now press stop. We can see that the setting is practically within the tolerance zone. We can also print the report. Here is our graph. It shows the tolerances and the adjustment results. In geometry adjustment mode and turbo boost mode, there's a function to check geometry play. In this section, we can evaluate the wear condition of the turbocharger's geometry. Electric actuator. 80. Here we set 95. Press start. The clearance is only 2%. This is a very good indicator. Inspecting valve N75. We are now connecting the required connectors. It is essential to close the valve. This is our number. This is the working valve N75's characteristic. The red line is acceptable. Let's take a look at the characteristics of the defective valve N75. We have number 1 here. It's defective. This one is faulty. Report printing is available. The N75 check function is included in the Turbo Boost program. The valve is illustrated here as well. Similar check here. We can also print the report. Startup window. The button should light up green. The service engineer mode is starting. Next, if we press Next, we access the graph mode. Right here. To choose the turbocharger, click the Load Test Plan button, the button for saving the test plan. We click the disk icon to save. Print button. When we have created some graphs, we can print them out. The check function for N75. The function for checking the geometry clearance of the turbocharger. Configuration of the expenses for a specific point, meaning the adjustment of the stop. And the graphics mode is available. In this mode, we have the window displaying the specifications of the turbocharger and the car it is fitted to. In particular, the model of the turbocharger, its number, that is, its name, serial number, diesel, engine specs, diesel or gasoline, displacement, horsepower, max power RPM, max turbine wheel diameter, max compressor wheel diameter, number of valves per cylinder, height above sea level. Here is the tolerance, but according to established specifications. And the result in kilograms per square centimeter, that is, in bars. Consumption in kilograms per hour, the graphs. We will load the first turbocharger we find. What is the significance of this machine? This machine can adjust the geometry of the turbocharger according to the test plan, based on the saved characteristics. That's one. And secondly, we can see in which mode our turbocharger operates. In the mode of its maximum efficiency. That is this little bump. It indicates the setting at which the turbocharger achieves its peak performance. You can load a different one. Here we see the bump. Geometry adjustment is visible. Specifically, it's the stop adjustment. Stop setting. This is the stop. It shows how the turbine inflates at the stop and reaches maximum power. Turbochargers can also be set up with a hump, meaning they can transition through maximum power mode or operate without it. This turbocharger is configured for maximum power mode. By adjusting the stop, we can either increase or decrease the turbocharger's power based on these graphs. Thus, we can observe how high or low the back pressure is on the hot snail supply. Additionally, when considering electric actuators, there are 3 types of settings available for them. In maximum efficiency mode, we can adjust the geometry of this turbocharger. A hump may form here. However, the turbocharger is currently set to maximum efficiency according to this test plan. Electric actuators can also be adjusted by percentage, specifically up to 90%. 90 to 95%. Here are the 95% we have. We can see what the back pressure is. If we take a pneumatic actuator, it is evident that this turbocharger is calibrated by transitioning through the peak power point. How to read these graphs in general. At the bottom, we have vacuum. at what vacuum position, which mode corresponds to the setting, the transition point during geometry movement. That is, we can see that the point of maximum efficiency is around 0.45. It's 0.45. This is around 300, 290, 300 millibar. If we aim to tune this turbocharger to maximum efficiency without crossing that point, we can set it to a back pressure near 300 millibar, effectively eliminating that bump. The turbocharger will be tuned for maximum efficiency. This rule works in practice, but not always perfectly. Turbochargers exceeding 2.2 liters in volume are considered relatively large for cars. The majority of these are calibrated for maximum efficiency. Turbochargers of 2 liters or less. Typically, they are adjusted with a small bump. This adjustment is not very precise. Since the turbocharger's main job in a car is to generate maximum boost. In principle, it can be said that the turbocharger can be tuned to the point of maximum efficiency. Thus, this can guide turbocharger tuning without a test plan. That is, with a deliberately removed characteristic. It can be said with 90% certainty that any turbocharger can be installed here, and adjustments can be made without a test plan. This software has the GEO-BOOST 2000 machine database integrated. To enter this database, you must navigate to the geometry support settings. Press the load button to access a database of 6,000 to 7,000 turbochargers. Choose the needed number to select the right turbocharger and adjust it based on the geometry database. In this case, we will see how this adjustment appears in dynamic mode. We have the following equipment. For connecting oil to the turbocharger, there are 8 adapters for different threads. There's also a hose that can act as an outlet, meaning it can be arranged this way. And we connect the oil feed, oil drain. Here is the most common oil drain adapter. A universal adapter is also available, compatible with all similar turbochargers. For the drain, there is a specific type of mounting available. Adapters for oil discharge are available. These are the plugs available for turbochargers with a collector. Rubber seals for them. You install one of these adapters on the inlet pipe. The plugs can be pressed down by means of manual clamps. You can use either type depending on convenience. For connection purposes. For the hot section, there are 2 main universal adapters for the compressor section that can be installed. They can accommodate any arrangement of holes, 3 or 4. These pedals are movable, and there are such elongated holes here. This makes life much easier. For various situations, there are 3 types of adapters available. They can also be used for fastening, just like a bolt connection. Also to speed up the process, you can use such clamps. This is another adapter for the compressor section. Various sub-diameters can be made. Pipes for the compressor section are also present. They can be installed or replaced. You can use this one. You can put this one in place. A spacer can be inserted inside. And this is inserted here and into the turbo compressor. There is also this type of adapter, which is used to connect the compressor. So, like this. And a clamp. The machine's geometric section also includes various adapters. For installing the turbine, there are different spacers that can be changed. For a small turbo, for a larger turbo. This is how they are changed. Rubber rings can be installed here. This is how the compressor is set up. For calibration, a calibration plate is installed. Here is the face. This is marked as the top part. You can use any fasteners you have on hand for mounting.